Hello students, good evening. Welcome to today's Fluid Mechanics Crux Conclusion Synopsis Classes. In fact, the basic idea of conducting these Crux classes is, first of all, let me introduce myself. This is Sekhar from Msigma Gokulam, one of the senior most teachers across India. And the main idea of conducting these Crux classes is having understood the fundamental basic concepts from the previous videos which I have already uploaded for the fluid mechanics in our Msigma Gokulam app. Students are advised to first go through all the video classes which I had given and which has been uploaded in the Msigma Gokulam app, and then come to these Crux classes. That is the best idea. So that the main idea of conducting these Crux Conclusion Synopsis classes is you can clearly understand the concept one after another, which are connected, because in fluid mechanics there are certain topics which are interlinked or interconnected. First you have to learn one topic and then next topic, like that. You can connect all these concepts in a sequential manner, and you can apply those concepts in the examination very quickly. So the main idea of conducting these Crux classes is to have a thorough revision of all the fundamental basic concepts required to solve any question that is asked in GATE examination. Our prime objective is to face any kind of GATE question that is given from this subject. In fact, in the fluid mechanics, the weightage will be around 7 to 8 marks in the mechanical syllabus. In the civil syllabus, it may be slightly lesser, around 6 or 7 marks. But for both civil engineering and for mechanical engineering, this is a very important subject, fluid mechanics. So, welcome to this Crux Conclusion Synopsis classes. So after completing these Crux classes, you would be able to solve almost any problem with confidence, whatever you are attempting in the GATE examination. So I will be quickly revising the basic definitions of the fluid properties, because in the fluid mechanics, the basic properties we have to first of all notice. What do you distinguish between a fluid and a solid? Fluid is a part of the matter which undergoes continuous deformation even under the action of a slightest shear force or shear stress. Even there is a slightest shear stress acting on a fluid element, it cannot be at rest. It should keep on deforming as long as that shear force or shear stress is acting. Whereas if it is a solid, it requires a lot of shear force to be applied onto the solid, but the deformation is not continuous, because under the action of a huge shear force or a shear stress, the solid body deforms very little, and once you remove that shear force, the body would be able to regain its shape and size, because that is the elastic nature of a solid. But when you come to the fluid, even if you act a slightest shear force, the fluid keeps on deforming or keeps on flowing. So that is why in case of the fluid mechanics, we always call it as a rate of strain, whereas in solid mechanics or the strength of materials, we always call only strain. In case of the solids, it is all about the strain, whereas in case of the fluids, it is always named as the rate of strain. We have the rate of strain here in fluid FM, whereas in solid mechanics, it is simply a strain there. So the fundamental main properties which we generally talk about in the fluid mechanics is mass density rho, which we know very well defined as mass per unit volume, and specific gravity rho of the fluid divided by rho of the standard fluid, that is water. There is a specific gravity which is also known as relative density. Okay. And the third and the foremost important is W, specific weight. This is the very important property of the fluid, which we discussed throughout the subject. Weight per unit volume, weight by volume, that is, which can be also be called as rho g, specific weight, or which is also called as the weight density. Okay, if this is a mass density, this is a weight density. Okay, W is a rho g. And W of the water we are supposed to remember, because water is a standard liquid which we see throughout the FM subject, 9.81 kilonewton per meter cube. How do you define the specific weight? Weight per unit volume of the liquid or fluid. Generally, when I talk about fluids, it includes liquids, gases, vapors, everything. Blood is a fluid, air is a fluid, water is a fluid, kerosene is a fluid, mercury is a fluid. Whatever that is able to flow is a fluid. All liquids, all gases and all vapors can be all can be treated as a fluid, because it is a very, very important science which envelops so many branches of engineering: mechanical, civil, metallurgical, mining, so many, chemical, etc., etc. About 5 to 6 branches of engineering will cover this subject. So this is the specific way. Then comes the most important property, which we call it as the viscosity. Viscosity, one we should thoroughly understand, because there are definitely problems. They were given, they will be given again in the GATE examination. Many times the questions were asked regarding the viscosity. What is this viscosity? Viscosity is the property of the fluid by virtue of which there is a resistance offered by one layer of the fluid over its adjacent layer against the relative motion. See, you must have noticed that some fluids could easily flow. Air can easily flow from one location to another location. Water cannot flow as easily as that of the air. Water also flows, but not as easily as the air. Supposing you have a lubricating oil, viscous oil, that flowability is very, very less, because that oil will be suffering more and more resistance against its motion. What will offer that resistance means fluid itself. Viscosity is a basic property of any fluid by virtue of which there is a resistance offered by one layer of the fluid over its adjacent layer against the relative motion. As one layer of the fluid is sliding over its adjacent layer, you observe there is a shear resistance or a shear force being felt as one layer of the fluid is sliding over its adjacent layer. So as the fluid is moving, there is a resistance felt between any two adjacent fluid layers which are sliding one above the other. That resistance only we call it as the viscosity. To understand that property called viscosity, the best way is to take the Newton's law of viscosity. Supposing if you take two plates, I am just explaining about the fundamental law of viscosity called as the Newton's law. Newton's law. If you understand the Newton's law of viscosity, you can do so many problems of the FM. There are two plates which are kept at a distance of y. There are two plates which are kept at a distance of y. The A is the area of the plate and bottom plate is fixed. Bottom plate is fixed. And the top plate, I am exerting a force P and I am able to pull it, the top plate. The top plate is being pulled moving with a constant velocity v. By exerting a force P, the top plate is being pulled rightwards, which is moving with a constant velocity v. The bottom plate is fixed. The gap between the plates is y. And you may definitely think that if there is a force exerted on the plate must move with an acceleration, but it is moving with a constant velocity. When it is moving with a constant velocity means acceleration is 0, because rate of change of velocity is acceleration. But that means the plate is moving with a constant velocity, which means that its acceleration is 0. When its acceleration is 0, according to the Newton's second law of motion, F is equal to ma, when a is 0, net force is also 0. So that means this applied force P might have been cancelled, might have been nullified by equal and opposite force exerted on the top plate. I have applied force P. That applied force P might have been cancelled or nullified by the opposing force, so that the net force acting on the plate is 0. When the net force acting on the plate is 0, acceleration will be 0. When acceleration is 0, the plate will be moving with a constant velocity. So that opposing force is exerted over the top plate is because of the viscous nature of the fluid. How that viscosity will be coming into picture, we can understand here. See, because of the viscous nature of the fluid, every fluid will have viscosity. Because of the viscous nature of the fluid, there is one layer of the fluid attaching itself onto the top plate that cannot slip from the plate. There is that yellow color layer, there is one layer of the fluid which is attaching itself to the top plate. Because it cannot slip from the plate, that is called as a no slip condition. No slip, it can't slip from the plate. That layer would have exactly the same velocity as that of the plate V. Because in a similar manner, there is one layer of the fluid that got attached to the bottom plate. It cannot slip from the plate. Because the plate is stationary, that layer also will have a zero velocity. This is zero velocity. The bottommost layer is having zero velocity. Topmost layer which is attaching to the top plate has got a velocity v. The different fluid layers at different heights would have different velocities, creating velocity gradients. So this length of the arrow, is indicating to some scale the velocity of the fluid layer at that particular height. If y is the coordinate, this is the coordinate, bottommost layer which is attaching to the bottom plate has zero velocity. There is no length of the arrow. Next layer has got more velocity. Next layer has got still more velocity. So different fluid layers are having different velocities. At any height y, if the velocity of the fluid layer is u, there is a velocity gradient. Velocity gradient. That point you have to keep in mind. When you talk about the Newton's law of viscosity, the velocity gradient is the word we have to keep in mind. What is that velocity gradient? The slope of that, the slope of this curve, dou u by dou y. This is called velocity gradient. Okay, according to the Newton's law of viscosity, shear stress or viscous stress, shear stress means viscous force per unit area is directly, this is also called tau, is directly proportional to the velocity gradient, and the proportionality constant is called as dynamic viscosity of the fluid. The proportionality constant is called as, mu is known as a dynamic viscosity of the fluid, which is a property of the fluid. The other name of that mu is also known as absolute viscosity, also called as a dynamic viscosity. This is the units for the mu will be Pascal second or Newton second per meter square. Stress units are Pascal, right? Dou u by dou y is called velocity gradient. What do you mean by velocity gradient? If you just take a differentially small height dy, for that dy difference height, what is the difference in velocity of the fluid layers? Because as one layer is moving, next layer will be moving with a different velocity, next layer will be moving with a different velocity. So different fluid layers are having the different velocities. Bottommost layer has got a velocity 0, the topmost layer has got a velocity v. Okay, different fluid layers are having different velocities. Velocity gradient means for a distance of dy, differentially small change in y, what is the change in velocity? That is called as the velocity gradient, also known as rate of angular deformation. This velocity gradient has got different names. That this is also called as rate of angular deformation or rate of shear strain. Both mean the same. Rate of angular deformation or rate of shear strain or rate of shear strain. I already said strain is the business in strength of materials or solid mechanics. Rate of strain is the business in fluid mechanics. That is, you can say the Hooke's law of elasticity in what you study in strength of materials or solid mechanics, stress is directly proportional to the strain. But yeah, the identical law here, it is called as in Newton's law of viscosity, which is called as stress is directly proportional to the rate of shear strain. There it is only stress versus strain. Here the stress versus rate of shear strain. Please note that Hooke's law of elasticity and the Newton's law of viscosity are similar, but in two different subjects. One is SM, the other is in FM there. Right. Mu is the dynamic viscosity, is mu by rho. It is called as another important property called as kinematic viscosity of fluid, which is also a property. Kinematic viscosity, which is also a property. Dynamic viscosity divided by the density. Its units will be, we have to be very thorough. I would always suggest, throughout my experience of 30 years, I always suggest, I'm having a 30 years of teaching experience in GATE and ES, etc. Total my teaching experience is more than 35, out of which around 25 to 30 years I was in GATE coaching. I always advise the students, please be strong about the units. Once you are strong, once you are confident about the units, you will never go wrong with the problems. I can definitely say you can easily, by looking at the problem itself, you can easily adjust yourself via units, and you are sure of getting the exact answer. If you are weak in units in any subject, not only FM, I can say heat transfer, thermodynamics, or even the strength of materials, units try to keep a hold on that. Okay, this is in meter square per second, or here that is a Pascal second is the unit of mu. In 1 poise is also the 1 poise the unit of mu, which is equal to the 1/10 of Pascal second. 1 poise is 1/10 of Pascal second. Similarly, this is the unit for the mu. Similarly, one Stoke is the unit for the kinematic viscosity nu. Mind that all these definitions are important in keeping in view for the another important subject of mechanical engineering called as heat transfer. In the heat transfer, the fundamentals of FM are very much essential, particularly in the convection heat transfer chapter. Okay, 1 Stoke is equal to 1 centimeter square per second. This is also unit of this viscosity. Okay, so these are the basic properties, and apart from that, there is another important property called as the surface tension, sigma. Surface tension, sigma. What is this surface tension? I hope you understood about the viscosity. Viscosity is the resistance felt between the fluid layers which are sliding one above the other. Viscosity is basically a force, a shear force, a non-conservative shear force. Whatever the work done against the viscous forces will automatically get converted into heat, and I can say it is some sort of an irreversibility. In thermodynamic point of view, the viscosity can be thought of as an irreversibility. I always suggest, dear students, whatever the doubts if you have, you are welcome to chat. I am looking into the system here, and you are free to ask me doubts by typing your doubts. I keep watching into the system there. I will be able to answer instantly and immediately. If you can post the doubt in this, you can type the doubts there. I am watching here, my system here, and viscosity is a property. There is no fluid having zero viscosity. If any fluid is having zero viscosity, it is called as an ideal fluid. Is there any ideal fluid? No. There is no ideal fluid in nature. All the fluids, including gases, all air, all gases, all water, everything, oils, everything have got viscosity. But some will have more. Lubricating oils will have more viscosity. But then generally what we see used in the journal bearings, etc. No? In all the vehicles, in all the machineries, we use the lubricating oils to reduce the wear and tear. They will be having a very good viscosity. Water has got viscosity, air has got low viscosity, but some viscosity is there. No fluid has zero viscosity. If any fluid has got that, it is called an ideal fluid, also known as the inviscid fluid. Is there any fluid in nature? No. No fluid is ideal in nature. It is only a theoretical imaginary fluid, ideal fluid is. Right. And do the viscosity be changed by the temperature? Yes. For liquids, viscosity decrease with increase of temperature. As you increase the temperature of the oil, its viscosity gets reduced. Whereas for the gases, as the temperature of the gases increase, viscosity also will increase. So for gases, they respond in a different way. For liquids, as the temperature increases, viscosity will decrease. Okay, then the surface tension. What is this surface tension? See, you must have seen that on all the water surfaces, particularly dirty water, you must be observing some insects keep walking on that dirty water. If you place gently a small pin in the water, that will be able to float. So then what is able to balance the weight of the pin or the weight of the insect? What is able to balance that weight? What is balancing the weight of the insect which is walking on the surface of the mud water, or the weight of the pin gently placed over the surface of the water? It is the tension prevailing in the surface of the water. Surface tension you will always see between a surface of liquid and the surrounding air. Okay, a surface of the water and the air, or it need not be water, it can be any liquid. Between any liquid versus gas, you may observe the surface tension phenomenon. Why this surface tension phenomenon? Because of the intermolecular attractive forces called cohesive forces. Cohesion forces among the liquid molecules are the main reason behind the surface tension phenomenon. Okay, and the tension prevailing in the surface of the water in contact with the air, this is water, this is all water, right? This is air. The tension prevailing, supposing this is a water, if you gently place a pin, the tension prevailing in the surface of the water would be able to balance the weight of the pin. So this surface tension is owing to the intermolecular attractive forces. I could explain you like this. If you just take the interior molecule, it is being pulled equally from all the sides. The net force acting on that molecule is zero. If you just take the interior molecule, it is being equally pulled by all the molecules surrounding that. Therefore, the net force acting on that interior molecule is zero, because this cancels this cancels this would be cancelling this. But if you just take the molecule prevailing in the surface of the water, this is being cancelled by this. But how about this downward pull? How about the downward pull? So all the surface molecules prevailing in the surface of the water, all these molecules prevailing in the surface of the water, all the molecules prevailing in the surface of the water are being pulled with a net downward force because of the intermolecular attractive force called cohesion. As such, as a result, the surface of the water in contact with air, it is like a stretched rubber membrane under tension. Just if you just look at a rubber sheet, pull it from all the a thin rubber sheet, pull it from all the sides, one person that side, one person this side, pull it. If you just touch it at the center of the rubber sheet, you will see some. If you gently place one small stone on that, that stone can be hanging on that stretched rubber membrane, which is being pulled from all the sides. So what is balancing that weight of the stone? The tension prevailing in that rubber sheet. In the same manner, because of the net downward pull acting on all the surface molecules, the surface of the water in contact with the air is like a stretched rubber membrane which is under tension. That tension is known as the surface tension. So sigma has got the definition of force per unit length. Force per unit length prevailing in the surface of water, prevailing in the surface of liquid. Prevailing in the surface of liquid, it's having the units of, sigma has got the units of Newton per meter. Is one of the gate question that is being asked. What are the dimensional formula? Newton is ml t power minus 2 divided by L gets cancelled, that is m t power minus 2. This is the dimensional formula for the surface tension, which is one of the gate question being asked. I suggest you to solve all the previous year's gate papers. Once your Crux conclusion and synopsis classes are over, are being conducted, you simultaneously solve all the previous gate papers. And once you are able to solve them with the concepts what you are learning from these Crux conclusion synopsis classes, you will feel more and more confident. In a lesser amount of time, you can attempt more number of questions in the gate examination, so that you would be able to get the best score in the gate examination. Okay, see, in the gate examination, how accurately you are able to do, that is one thing. Another important thing is how quickly you are able to do. Time management is a main thing, because it is a 3 hours examination, 65 questions there, and you very quickly you have to answer the question as quickly as possible, so that the maximum number of questions correctly you are able to answer. The time management is very, very important. For that, we have to immediately strike the moment you read the question, concept must strike in the brain. You should be able to apply it, get the correct answer, because there is a negative marking problem also there in the multiple choice. You should be exactly write the answer, get the answer. So for For that, striking the concept, these kind of a revising the fundamental concepts are very much important, for which these Crux conclusion synopsis will be very much helpful to all the students. Okay then, and this is the surface tension. I'll just give the example for the surface tension. 3 examples I will give it. If you just look at the water droplet, because of the surface tension, the pressure inside the water droplet is more than the atmosphere. By what extent it is more than the atmosphere, I can say that is called as the gauge pressure. Its formula is 2 sigma by r, where r is the radius, of the droplet. Okay, Newton per meter square. This is a gauge pressure. What do you mean by gauge pressure? Any pressure in excess of the outside local atmospheric pressure is called as a gauge pressure. Whenever I talk about a gauge pressure, it means that by what extent the pressure is more than the outside local atmospheric pressure, it is called as the gauge pressure. The gauge pressure inside the water droplet is given by 2 sigma by r. Similarly, the gauge, and this pressure has built up purely because of the surface tension prevailing in the surface of the water in contact with the air. Similarly, if you just look at the soap bubble, a thin soap bubble, this is air, this is air. See, I once again advise all the students to kindly look into my fluid mechanics classes uploaded in the Msigma Gokulam app. And before attending the Crux classes, please go through all those video classes, and this Crux conclusive synopsis classes will be very much useful for you. To follow up these Crux classes, the prerequisite is all the students are advised to go through my fluid mechanics classes, which were already uploaded in the Msigma Gokulam app. I'm just reading your doubts there. Is viscosity is associated only with fluid which is in motion? Very much right. Viscosity is associated, Mr. Fenil, yes, viscous forces will come into picture only when the fluid is in motion. For a fluid at rest, there are no viscous forces being felt. For a fluid element under rest, there are only stresses which are the normal stresses. There are no tangential stresses. So that question is also being asked in the GATE examination. A fluid element under rest is not subjected to any kind of viscous stresses or tangential stresses, but the fluid element at rest is subjected to only the normal stresses, which are also called as hydrostatic pressure. That is why if you just look at the Morse circle, if you just draw the Morse circle, the Morse circle will be, this is the shear, this is the normal, okay. So there are no shear stresses for a fluid element at rest. This is the state of stress. Morse circle reduces to a point. Morse circle concept is very important in the strength of materials. For a fluid element at rest, the Morse circle shrinks to a point. Morse circle is a point, because there are no shear stresses acting on the fluid element at rest. There are stresses, but are of normal nature, of compressive nature. That is why on the negative x-axis I have marked. These are normal, these are tangential. No tangential or viscous stresses. Tangential stresses, viscous stresses all mean the same. I hope you got cleared. Mr. Fenil, does static fluid also has resistance between layers? No, there are no resistance between the layers, but there will be a normal stress which is of compressive stress. Okay, that is also called hydrostatic pressure. A fluid at rest is subjected to only a normal stresses, which we also call it as the hydrostatic pressure. Pressure is a normal force. Okay. Any more doubts? Please keep joining into the chat box. Right. Now this is air, this is the soap bubble. For the soap bubble, the P gauge, the gauge pressure inside the soap bubble is given by 4 sigma by R. Please remember this formula. Here it is 2 sigma by R for the droplet. It is 4 sigma by R for the soap bubble. Okay. Because why it is 4 sigma? Because there is a surface tension here. There is also a surface tension here. Sigma is a sign for the surface tension. One more example is a cylindrical jet of water. The cylindrical jet of water, that again you have the gauge pressure. The gauge pressure is given by sigma by R. 2 sigma by R, 4 sigma by R, sigma by R, Newton per meter square. The 3 different situations. A cylindrical jet of water, water droplet and soap bubble. Okay. All these shapes are attributed to only the surface tension. Okay. I hope, please remember these 3 formulae. So in this point is also very important. A fluid element at rest is not subjected to any shear stresses or tangential stresses. No shear, no tangential, but there will be negative normal stresses, negative compressive nature. It is like this. For a fluid element at rest, this is the state of stress. All sides the pressures are hydrostatic pressure is same. This is the fluid element at rest. Okay, not under motion. Right. Now, having seen the surface tension, now I will introduce another property called capillarity, capillary rise. Capillary rise. Whenever you just immerse a thin glass tube, capillarity effect. Capillarity in English means a thin passage. A thin glass tube which is open at both ends is immersed in water. The water will rise. Water will rise. This is called meniscus. This is a meniscus. Water will rise. Because why? Because for water liquid molecules, the attraction towards the glass is more than towards its own molecules. That is why adhesion is greater than cohesion. Cohesion means the intermolecular attractive forces of the same liquid molecules is called cohesion. The extramolecular attraction between the molecules of the liquid and the molecules of the container, that is called as the adhesion. So paints are good adhesions, good adhesive agents. When you put a paint, you can't take it out, right? Because it sticks immediately. That is called adhesive nature. So here the water has got more attraction towards the glass than towards its own molecules. That is why it is rising. If the same glass tube is immersed in mercury, this mercury will dip. This is called capillary rise. This is called as capillary rise. This is called as capillary depression. Capillary depression. Why? Because in mercury, as you all know aware that mercury won't wet anything, because it has got a very poor adhesive nature and highly cohesive nature. Its attraction, its own molecules is far more greater than the attraction towards the container in which it is present. Okay, that is why mercury is dipping. Mercury is dipping. You see, the meniscus is like this, downwards. It is here the meniscus is upwards. This is a capillary depression. This is here the cohesion is greater than adhesion. So please note that these kind of an adhesion or rise or the dipping you will see only when the diameter of the glass tube is sufficiently small. Thin, it must be thin glass tube. If you take a thick glass tube, you don't see any effect there. And whether it is a capillary rise or capillary depression is this formula. You have to remember 2 sigma cos theta divided by WR. As you notice that where R is the radius. Where R is the radius of the glass tube. Smaller the radius of the glass tube, more the more the capillary rise. Capillary rise. Please remember this formula. Sigma is the surface tension. Theta is this angle. For in case of the this theta, in case of the 130 this is, and for water we may take it as 0, and that is why if H is cos 130 is a negative, that is why H will be in depression there. You will get a H value negative. Okay, W is the specific weight, R is the radius of the glass tube. As you notice this, the radius of the glass tube, if it is smaller, the capillary effects will be predominant more and more. Okay, that point remember. Capillary effects you can see more only when the radius of the glass tube considered is sufficiently small. Practical examples is like this. The trees can take this nutrition from the soil through its roots, but the passages of the roots is very, very small. Through that water can, the tree can take the nutrition for its growth. Okay. Best example for the capillary effect. Smaller the passage diameter, more the capillary effects you can observe. You can see smaller the R, more the H. Then what is balancing this weight of the column is surface tension. See, the surface tension only is balancing the weight of this liquid column that is rising inside the glass tube. From the equilibrium of the weight of the liquid column with the upward surface tension force, we got this formula. By hitting the equilibrium condition for that weight of the liquid rising inside the glass tube, liquid is rising inside the glass tube. The weight of that liquid column is balanced by the component of the shear sigma surface tension force in the upward direction. The weight is acting downwards. The sigma surface tension force has got the vertical component. Both will be balancing each other. From that equilibrium, we got this formula for the capillary rise. Okay, right. We got the capillary effects also, capillary formula. And then very important phenomenon is vapor pressure and cavitation. Vapor pressure is another property which is linked to a phenomenon called cavitation. What is this vapor pressure? Whenever a liquid, supposing this is liquid is there. In the liquid molecules keep moving, right? Randomly. They leave the free surface of that liquid and they get accumulated in the volume available above that free surface. So these vapor molecules will exert a pressure while they keep going up and they are coming back. And under certain conditions, there will be one equilibrium attached, right? Molecules keep leaving the free surface and at the same time they are returning back. Okay. After certain time, equilibrium is established. That means the rate of leaving and the rate of coming back will be exactly same. So under that condition, saturated condition, the vapor collected in the above that liquid, the vapor collected above that in that volume will exert a pressure which is called as a vapor pressure. If this is the liquid, this is the free surface. Because the liquid molecules are in continuous motion, they leave this free surface of the liquid and escape into this emptiness. Okay. So all these vapor molecules keep getting collected in this emptiness and they keep going back also. They are leaving the free surface, some molecules are coming back. After a certain stage, there is an equilibrium established. That means the rate of leaving and the rate of returning of the molecules will exactly be equal. Under that condition, I say that the space is saturated with vapor molecules and the pressure exerted by the vapor molecules is called as a vapor pressure, which is very much linked to the temperature, which is strongly linked to the temperature. Higher the temperature, more the vapor pressure of the liquid. Okay. Then this vapor pressure is a property which is strongly connected to a phenomenon called cavitation. What is this cavitation? During the flow of a liquid in any pipeline, if the pressure at any location falls equal to the vapor pressure of the liquid corresponding to its local temperature, during the flow of a liquid in any pipeline, if at any point, if the pressure of the liquid falls to a value of the vapor pressure of the liquid, immediately the liquid begins to vaporize, keeps bubbling, okay, forming vapor pockets. When these vapor pockets are carried by the liquid and enter a location where they suddenly collapse, at some location they suddenly collapse and creating a localized pressure differentials, thereby damaging the surrounding solid surface. That phenomenon is called as a cavitation. I repeat once again, during the flow of a liquid, if at any point, if the local pressure of the liquid becomes equal to its saturation vapor pressure corresponding to its saturation temperature, I repeat once again, if during the flow of a liquid in any container or a pipeline, if the local pressure of the liquid becomes equal to its vapor pressure corresponding to its temperature, immediately the liquid begins to vaporize, forming vapor pockets. When these vapor pockets are carried into the high pressure zone, they collapse, forming a localized vacuum, and the surrounding liquid rapidly rushes there to fill that vacuum, thereby damaging the surrounding solid surface, and that phenomenon is called as cavitation. Cavity means a small hole, as if you are hitting the surrounding solid surface with a sharp knife. You will see the tiny cavities on the solid surface. So vapor pressure is a property connected to that cavitation. Then coming to the another important property called bulk modulus. Very important property, the bulk modulus and compressibility. Because there is one chapter in particularly for the mechanicals, compressible fluid flow. Okay, in that particular chapter, this bulk modulus K and compressibility C are very much important properties. Whenever you are talking about the compressible fluid flow, this compressibility or the bulk modulus are very important properties. What is this bulk modulus? Supposing if you just take a fluid element, liquid element say, or fluid element, if you exert the pressure, equal pressure on all faces, cubical element of all the faces, on all the faces, if you exert the same pressure, the volume of that cubical fluid element may decrease. As you exert the pressure on all the 6 faces of the cubical fluid element, the volume may decrease. So as a result, the pressure inside that cubical fluid element will increase. So the volumetric K is defined as volumetric stress divided by volumetric strain. Similar definition you may see in strength of materials also, but there are 3 moduli of elasticity. Modulus of elastic modulus, 3 modulus are there: shear modulus, bulk modulus and Young's modulus. But here we talk about only one modulus in fluid mechanics, volumetric stress by volumetric strain, delta minus delta P by delta V by V. That is, bulk modulus can be written as change in pressure divided by change in volume divided by original volume. Its units are megapascal. This is the formula for the bulk modulus. And what is the real use of defining this bulk modulus or compressibility? Fluids are broadly can be divided into 2 categories: incompressible fluids and compressible fluids. For the incompressible fluids, any doubts if you are having, you may kindly requested to post them in our chat box so that I would be able to answer. For all the incompressible fluids like water, all the liquids by default are incompressible. All the liquids are by default are incompressible because for such fluids this K value is very high. Liquids are incompressible, all liquids like water, oil are incompressible. For incompressible fluids, K is very high. Therefore, compressibility is low. What is this compressibility? Reciprocal of the bulk modulus is called compressibility. For all the incompressible fluids, K is very high, C is low. Contrary to that one, for gases, bulk modulus of velocity is low and compressibility is high. Gases their volume can be easily reduced by exerting pressure, but for liquids it is not that easy, very difficult. Water density is 1000 kg per meter cube. Okay, can the density be changed by exerting pressure? Means no, not at all. Density is practically a constant for the incompressible fluids. For all the incompressible fluids, density is practically a constant. For the compressible fluids, density may change with the pressure. So that is how we distinguish between incompressible fluids and compressible fluids. Compressible fluids example are gases. But there is one again exemption. Even the gases also can be treated as incompressible if the density is almost same. It won't change with pressure. If the density changes are negligibly small, 1% change in density or 2% change in density, even the gases also can be treated as incompressible. Okay, mind that. Even the air can be treated as incompressible. Air is a gas. It can be treated as incompressible provided if the density changes are around 1 or 2% changes, it can be neglected and density can be treated practically a constant. That means I can say for the incompressible fluids, density is not a function of pressure, whereas for the compressible fluids, density becomes a function of pressure. Best example is supposing air is coming through a ceiling fan. Would you call that flow of air through the ceiling fan as compressible or incompressible? My answer will be incompressible. Then you may be surprised. The flowing fluid is air, then it should be treated as compressible. No, need not be. It can be treated as incompressible because the density changes of the air as it flows through the ceiling fan is not even 1% or 2%. So you can neglect it. As long as the density changes of the fluid are less than 5%, we can treat even the gases flows also as incompressible. Keep that point in mind. In fact, there is a latter I am going to discuss in the compressible flow. If the Mach number of the flow, here becomes the very important dimensionless number called as the Mach number when you think about the compressible fluid flow. If the Mach number of the fluid flow is less than 0.3, mind that. If the Mach number of the fluid flow is less than 0.3, all fluid flows can be treated as incompressible. We can neglect the effect of compressibility effects. You can neglect the effects of density changes. So we can treat any fluid flow as an incompressible if the Mach number of the fluid flow is less than 0.3. So that 0.3 is a border. Less than 0.3 incompressible, more than 0.3, if Mach number is more than 0.3, it is compressible fluid, I can say. That is a borderline, 0.0.3. How do you define the Mach number? Velocity of the fluid divided by, Mach number is very important definition in fluid mechanics. Mach number is velocity of the fluid divided by velocity of the sound in the fluid, sonic velocity. Okay, this is a very important number in the compressible fluid flow. Definitely in the recent GATE examination, very regularly the questions are coming on this Mach number. In GATE 22, 23, 24, every year one question being asked on that Mach number in the mechanical syllabus. Okay, so these are all the main important properties we have discussed, and let me solve some of the important questions there which is asked in the Before going to that one, I will define fluid pressure and its measurement. The main important points regarding the fluid pressure, let us know. Every fluid will exert a pressure on its surroundings or on the solid boundary with which it is in contact. How do you define the pressure? Limit normal force. Normal force per unit area is called as fluid pressure. Its units are Newton per meter square or Pascal. Why do any fluid exert pressure? Because fluid contains molecules which are in motion, continuous motion. When these fluid molecules collide with the walls of the container, they exchange momentum, they exert force, and that normal force per unit area is called as the fluid pressure. In our body, there is a liquid flowing, blood it will exert the pressure. Outside our body there is an atmosphere which is exerting pressure, which is called an atmospheric pressure. So because so all the surrounding atmosphere is exerting a pressure on my body, which is called as an atmospheric pressure. One standard atmospheric pressure is 101.3 kilopascal, which is equal to the 76 centimeters of mercury or 10.33 meters of water. Anything standard atmospheric pressure at the mean sea level, at the mean. Okay. But as you go to the higher and higher altitudes in the atmosphere, the atmospheric pressure keeps decreasing. Okay. As you go to the higher and higher elevations in the atmosphere, the atmospheric pressure keeps decreasing. This is the value at the MSL or the mean sea level. Right. If any pressure is more than the atmosphere, it is called as the positive gauge pressure. If this is the atmosphere, if any pressure is more than the atmosphere, that is called as the positive gauge, corresponding to which you have the absolute pressure can be thought of as atmospheric pressure plus gauge pressure. This is how we define the absolute pressure. If any pressure is measured with reference to the atmospheric pressure, it is called as a gauge. This is an absolute zero pressure. Sometimes the pressure may be lesser than the atmospheric pressure. Example, the condenser of a steam power plant, you will see the pressure less than the atmosphere. In such case, sometimes any pressure in any device may be much lesser than the outside atmospheric pressure. By what extent it is lesser than the outside atmospheric pressure? It is called as a vacuum pressure, or which is also called as a negative gauge. This is a positive gauge because it is more than the outside atmospheric pressure, the surrounding local atmospheric pressure. If it is more than the surrounding local atmospheric pressure, it is called as a positive gauge. If it is lesser than the surrounding atmospheric pressure, it is called as a negative gauge, also known as the vacuum. Then the absolute pressure will be atmospheric pressure minus vacuum. This is called as the absolute pressure. So anything absolute pressure is reference to the absolute zero. Okay, right. So we understood what is the meaning of the positive gauge, negative gauge, what is how to calculate the absolute pressure, etc. Okay, then the Pascal's law of hydrostatic pressure. If this is the liquid, for a fluid at rest, the pressure at a point is same. The pressure exerted at a point is same in all the directions. Px is equal to Py is equal to Bz, where x, y, z are three mutually perpendicular directions chosen arbitrarily. 22. So the pressure exerted at a point, in a static mass of fluid is transmitted uniformly in all the directions. That is called as a Blaise Pascal's. Pascal's law states that the pressure exerted at a point in a static fluid, that is at rest, is transmitted uniformly in all the directions. That means the pressure is uniform along all the directions, where x, y, z are taken arbitrarily, any three mutually perpendicular directions chosen arbitrarily. I repeat the Pascal's law. The pressure exerted at a point is transmitted uniformly in all the directions. Px is equal to Py is equal to Pz. The pressure at a point is uniform along all the directions. That is called Pascal's law. There is another important law called as the hydrostatic law of pressure variation. Hydrostatic law of pressure variation. I welcome all the students to kindly chat into the chat box so that I would be able to answer all the doubts. In fact, even after the class also, you have the mechanical engineering community WhatsApp group is there we have. You can directly post the questions there. I would be able to answer in that WhatsApp groups also. Otherwise, I will give my number. You may ask me the doubts in my WhatsApp number also. We have the various ways of in Msigma Gokulam, whereas we got the various means, various ways of clearing the students' doubts through WhatsApp groups or Telegram groups or the personal chats. There are many ways we are able to can reach out to the students and clarify your doubts. And this law states that if this is Z direction, this is X, this is Y. In a static mass of fluid, as we go deeper and deeper, the pressure keeps increasing, whereas dou P by dou X is equal to 0, dou P by dou Y is equal to 0. There is no change in pressure intensity as you go along the X direction, as you go along in the Y direction, but it changes only in the Z direction. Dou P by dou Z is equal to minus rho G or minus W. Z is the positive direction upwards. What is the minus sign shows? What is the minus sign shows? As you are going in the upward direction, the pressure intensity keeps decreasing. As we go in the deeper and deeper, the pressure intensity will be increasing. Suppose if you just look at these two locations, this is 1, this is 2. Where will be the pressure will be more? At 2, because all the deeper points in a static mass of liquid are subjected to the more pressure intensity. P2 is greater than P1. Or I can say P2 minus P1 is equal to W into the difference in heights, WH. P2 minus P1 is equal to WH. So many kilo. Generally, pressure units you always mention only in kilopascal. Always, when you are using the Bernoulli's equation or Euler's equation or whatever it is, try to maintain the pressure units only in kilopascals. So, as you go, the pressure difference between two locations which are at a depth of vertical depth of h is directly proportional to the h. W is the specific weight of the liquid. This is called as the hydrostatic law of pressure variation. That means if you just take any 2-3 locations which are at the same depth, they are all subjected to the same pressure intensity. At all these points, the pressure is same. But as you go deeper, the pressure intensity keeps on increasing. At the bottommost point, that is the bottommost location of the container, the pressure intensity is the highest. You can put it like this also. For example, this is a liquid free surface. This is a symbol. Liquid is having some specific weight W. Now, if you just take a location here, which a depth of h from the free surface, this symbol means atmospheric pressure is prevailing. Though P1 gauge can be simply written as WH. The pressure at a location inside a static mass of the liquid having a specific weight W, kilonewton per meter cube. The pressure at this location is calculated by multiplying the depth of the point with the specific weight of the liquid. I will give another example. Suppose that we got two different liquids. This is W1, this is W2, this is a free surface. Two different, this is one liquid, this is another liquid. Say this depth is H1, this depth is H2. Now I want to calculate what is the pressure here. P gauge, how much is that? I would like to know. What is the P gauge? This is the free surface. So what is the pressure prevailing here? P atmosphere. This symbol is for the free surface, P atmosphere. So P gauge here is nothing but from here it is coming. Here the atmospheric pressure you are going down. By what distance you are going down? By a distance of H1. W1, H1 up to here it come. From here to here plus W2, H2 kilopascal. This is the gauge pressure at this location. Sometimes specific weight may not be given directly, it may be given via specific gravity. We know that specific gravity is defined as specific weight of the liquid, any liquid, standard liquid, any divided by specific weight of the standard fluid, that is water. Any fluid, specific weight, if it is compared with water, what we get is the specific gravity, also known as relative density. Okay. Right, specific gravity of the mercury is 13.6. It is a dimensionless quantity. Please, I am waiting to see your chat box. Please, any doubts if you have, you may simply chat in the chat box with me. Right, now we know what is what pressure, how we know how to define a pressure, how the pressure varies with the depth. Pressure varies only with the depth. Okay. Now this particular principle of pressure variation we will be using to measure the pressure of any liquid in a container by using a manometry. Most of the questions asked in the FM, particularly in the first chapter, will be asked about the manometry. I write the manometry equation. What is manometer? It is a U-shaped U-tube manometer. It has two limbs, right limb and left limb. It may carry its own manometric liquid. It may carry its own manometric liquid. So it may be mercury, it may be water, it can be some oil, it can be anything having the specific gravity Sm. Sm means specific gravity of the manometric liquid. Suppose that this container has got some liquid having a specific gravity S, some oil. This is a manometric liquid, maybe mercury or a water, some other liquid, but whose specific gravity is known. Sm is the specific gravity of the manometric liquid, S is the specific gravity of the flowing liquid in a pipe. I want to measure the pressure at this location, Pa. How to get that? First you have to notice the difference in the manometric liquid levels. Right limb and left limb. This is Y, I suppose. If this is X. And we have to wisely select the datum line. For writing the manometric equation, we have to just select some datum line. When you select the datum line, condition is that one side of the datum line must have the same liquid. This liquid and this liquid should be the same. One side of the datum line. See this is all same, right? When you are selecting the datum line like this, what is the hydrostatic law of pressure variation says? In a static mass of a continuous same liquid, all the locations which are at the same depth are subjected to the same pressure intensity. In a continuous mass of the same liquid, all the locations, in a continuous mass of the same liquid, all the locations which are at the same depth are subjected to same pressure intensity. That means the pressure here and the pressure here is same, exactly the same. So that is the logic I would like to use to write the manometry equation. What my objective is what? My objective is what is PA? What is PA gauge? Gauge or absolute, whatever it is. I want to know what is a PA gauge in this pipeline here. That is my unknown. Okay. For that I am writing the datum line. So how to select a datum line? One side of the datum line you should have the continuous mass of the same liquid. Okay. Now because the pressure here and the pressure here must be the same, because it is a continuous mass of the same liquid which are at the same elevation, right? So I am equating the pressure heads in meters of water, along datum line. Equating the pressure heads in meters of water along the datum line. That means here the pressure and here the pressure is same. That means pressure head is also same. What is the difference between pressure and pressure head? Pressure is the force per unit area. If that pressure can be expressed as a column of any known liquid, that is called as a pressure head. See, for example, you have the atmospheric pressure 101.3 kilopascal. If that atmospheric pressure, if it is expressed as a column of water, it is 10.33 meters. If the same atmospheric pressure of 101.3 kilopascal, if it is expressed as a meters of mercury, it is 0.76 meters or 76 centimeters of mercury. Same atmospheric pressure, you can express it as a column of water, that is 10.33 meters, or you can express it as a column of a mercury, which is a 76 centimeters, or for that matter you can express as a column of some other oil whose specific gravity is known. What we have to just write, if P is the pressure, just divide with the specific weight of that liquid into which you want to express that pressure, that we will get as the pressure head. Pressure head, supposing if this is atmospheric pressure, if you divide with the specific weight of water, you will get 10.33. If this is a standard atmospheric pressure, if you divide with the specific weight of mercury, you will get 76 centimeters or 0.76 meters. So, any fluid pressure, maybe which is above atmospheric pressure or less than atmospheric, a positive gauge or a negative gauge, can be expressed as a column of any liquid of your own choice. Just like, for example, if this atmospheric pressure is there, if you divide with the specific weight of water, you will get 10.33. If the same atmospheric pressure, if you divide with the specific weight of mercury, you will get 76 centimeters. If you divide with the atmospheric pressure with some oil specific weight, you will get that atmospheric pressure as a liquid column of that particular oil. That means any given fluid pressure, maybe atmosphere or maybe more than atmosphere or less than atmosphere, that means either a positive gauge or a negative gauge, whatever it is, or absolute, whatever it is, if that pressure can be expressed as a column of any liquid of your own choice. I repeat once again, any fluid pressure, may be atmospheric pressure, may be a positive gauge pressure, may be a negative gauge pressure, may be an absolute pressure, which is given in kilopascal, can be expressed as a column of any liquid of your own choice whose specific weight is known. What we have to do, we have to divide that pressure with the specific weight of that liquid, known liquid, maybe mercury, maybe water, maybe oil, you will get some H. So that is the liquid, that column will be indicating that fluid pressure. So any fluid pressure can be expressed as a column of any liquid of your own choice. Got it? This is a very important point. Now, I want to express the pressure here as a water column, you see, in meters of water. Why in meters of water? Because water specific weight is very well known. Remember that 9.81 kilonewton per meter cube. That means here the fluid pressure I want to express as a column of water. Here gauge or absolute gauge, because here what is prevailing? Atmosphere. When it is atmosphere, what is the corresponding gauge? It is zero gauge. Corresponding to atmospheric pressure, what is the gauge pressure value? Zero. Because anything more than atmosphere only, it is a positive gauge, right? Here atmospheric pressure is prevailing, that is a zero gauge. That means zero gauge plus you are going down. When you are going down by a distance of y meters of this liquid column. Or what is that specific gravity? Sm. But that should be converted into the water column. Okay. For that we have to divide with the specific gravity of the water. Luckily, specific gravity of water is 1. Luckily, specific gravity of water is 1. That means you have converted the Y meters of the mercury column or manometric liquid column into the water column just by multiplying with the ratio of the specific gravities. You have converted the Y meters of this manometric liquid column into the water column by multiplying with the ratio of the specific gravities. Into what column you want to convert? Water column. That is why in the denominator I have kept the specific gravity of water. Luckily, specific gravity of water is 1. Please remember, specific gravity of water is 1. So all this is indicating so many meters of water. Where is the pressure? At this location. But here and here is the continuous mass of the same liquid which are at the same depth, therefore pressures are same, therefore pressure heads are also same. That is equal to, I am coming from this side, equal. If PA is the pressure at this axis of the pipe, gauge pressure, this gauge, I am talking about gauge, because everything we are doing with the gauge here. So that because we are doing this side from gauge, this side also we have to do it as a gauge basis. Gauge means what? Any pressure in excess of the atmosphere, it is called as a gauge. So it is PA is the gauge pressure at this location divided by specific weight of water, which I know very well. That is 9.81 kilonewton per meter cube. Specific weight of water, please remember, specific weight of water is 9.81 kilonewton per meter cube plus, this is indicating the pressure head here. And all the locations which are at the same depth are subjected to the same pressure intensity. Here and here the pressures are same because they are at the same elevation. Pressures are same, therefore pressure intensities are same, or pressure heads also same. Here and here same. But we are going down. As we are going down, pressure intensity will increase. As we are going up, pressure intensity will decrease. So because we are going down, plus X. But that X is the this liquid column of having a specific gravity, yes. X is the column of this liquid. But I want to express in meters of water, I am telling. How to convert that? X into S divided by specific gravity of water. Luckily, the specific gravity of water is 1. So this equation reduces to easily. Y into Sm, S of water is 1, is equal to PA gauge by specific weight of water. We already know specific weight of water plus X into S, because specific gravity of water is 1. We can easily calculate. I know the specific gravity of mercury, manometric liquid column. I know the specific gravity of the flowing liquid. I know Sm, I know the S, I know the X, I know the Y, I know the specific weight of water. What is the specific weight of water? Already given here, 9.81. You can easily get the PA gauge. The unknown pressure can be calculated. This is the basis for writing the manometry equation. If you thoroughly understand the manometry equation, 21. If you thoroughly understand the manometry equation, any problem, one simple point you have to keep in mind for writing the manometric equation. All the locations which are at the same elevation in a continuous mass of the same liquid are subjected to the same pressure intensity. Here the pressure intensity, here the pressure intensity is same. But here and here the pressure intensities are not same. Why? It is not the continuous mass of the same liquid. Up to here only this oil is there. Here it is a different liquid, right? Here and here may not be same. But here and here it is same because it is a continuous mass of the same liquid. Here and here it is same because it is a continuous mass of the same liquid. Okay. When you can see same elevations are having the same pressure intensities, because it should be the continuous mass of the same liquid. Here and here same, here and here same, but here and here not same. So for writing the manometry equation, keep the point in mind that as you are going deeper and deeper, pressure intensity will increase, number one. all the locations which are at the same depth in a continuous mass of the same liquid subjected to the same pressure intensity. One column of a liquid indicating some pressure intensity can be converted into the some other liquid column by multiplying with the ratio of the specific gravities. One column of liquid indicating some pressure intensity can be converted into the some other liquid column by multiplying with the ratio of the specific gravities. See, this y meters of this liquid column I have converted into the water column just by multiplying with the ratio of the specific gravities. The important precaution is write that specific gravity of that liquid into which the conversion is being made, because I want to convert this y meters of this liquid column into water. That is why in the denominator I have kept the specific gravity of water. Fine. Now you can calculate easily the PA gauge. Okay. So this is the base for writing the manometry equation. I will just try to write some problems here. Look at this. In given figure, if the pressure of gas in bulb A is 50 centimeters of Hg vacuum, 50 centimeters of Hg vacuum, and the P atmosphere is 76, P not rho, this is P. If this is P, if the P atmosphere is 76 centimeters Hg, then the height of the column H, this is how much is asking. It can be done in two different ways. One, I do it on a gauge basis, one I do it on the absolute basis. So we will get the same answer. First let me get based on the absolute. What is the pressure here? It is clearly given 76 centimeters of Hg. Clearly given that one. Here and here the pressure is same. Why? Because it is a continuous mass of the same liquid, mercury. So here also 76 centimeters of Hg, but here you are going up. So in the gas, here, everywhere the pressure is same. Please remember, in gases, the change of pressure with location, height, everything can be neglected. If somebody in this room is there, the pressure there and the pressure there is same. But in liquids, never neglect even the 1 mm height of a difference in elevation. In gases, you may neglect the change in elevation. You can think that the pressure here, the pressure here, the pressure here, everywhere same. So here 76 centimeters of Hg, here also 76 centimeters of Hg, you are going up. Therefore, PA absolute is equal to 76 centimeters of Hg. I am doing a based on the absolute basis, minus H is equal to, he has given the pressure in the gas bulb A is 50 centimeters of Hg vacuum. I already mentioned, if any pressure is, if this is atmosphere, it is given as 50 centimeters of Hg vacuum, negative side, right? Atmosphere is 76. So then this will be how much? 76 minus 50, 26 centimeters of Hg. So this will be 26 centimeters of Hg. Therefore, H will be 76 minus 26. This is 50 centimeters. Answer is B. Okay, 19. Fan on. Okay. Now on gauge basis I will do the problem on, this is on the absolute basis. On gauge basis I will get the same answer. See, here it is 50 centimeters of Hg vacuum is given in the gas bulb A. So what is the gauge basis here? If the atmospheric pressure, now what is the gauge pressure here? Zero gauge. Here, zero gauge, because corresponding to atmosphere, what is the gauge pressure value? Zero gauge. Here zero gauge means here also zero gauge. You are going up. Okay. You are going up means the pressure will decrease. By what distance you are going up? H centimeters here. Okay. And he has already given that here it is 50 centimeters of Hg vacuum, that is minus 50 centimeters vacuum only, negative gauge. Vacuum means negative gauge. Minus 50 centimeters. So H will be 50. On the gauge basis, this is this is how it done. And on gauge basis, this is on absolute pressure basis. In either way, we got the same answer. Here the zero gauge. That is here and here the pressure is same, zero gauge. We are going up. We are going up means pressure will decrease. That is why minus 0 minus H centimeters. He has already given the pressure in the gas bulb here is 50 centimeters Hg vacuum. Hg vacuum means negative gauge. That is why I kept a minus 50. Minus minus gets cancelled, H is 50 centimeters. So either you do it on the absolute basis or gauge basis. Same answer we got. Yeah, this is a problem on the manometry. An inverted U-tube manometer is used to measure the pressure difference between two pipes. This is an inverted U-tube. Okay. Generally, U-tube manometers, differential U-tube manometers are two types. One is normal. This is a normal. It is a normal type. But this is an inverted U-tube. Okay. Between two pipes A and B. Pipe A is carrying oil. This is oil. Specific gravity 0.8. And pipe B is carrying water. This is all water. This is pipe B, water. Densities of air and water are 1.16 and 1000. It is all. Pressure difference between pipes A and B is so many kilopascal. Okay. Up to here it is water. Okay. Now, I'll do everything, I'll do the business in the water column. That is, if PA is the pressure at this location, PA by W of water, it is the pressure head. If PA is the pressure there, any pressure can be expressed as a column of a liquid, that is called pressure head. Pressure and pressure head both mean the same. Pressure is given in kilopascal, whereas pressure head is given in meters. But what meters? Whatever the liquid specific weight you are dividing, that many meters. So this is indicating pressure head of oil at this location. Here and here same. We are going up. By what distance we are going up? 100 mm. That is 0.1 meters. 100 by 1000, 0.1 meters there. We are going up. That is why subtracting. What is that? This is oil column. I have to convert into the water column because we have already expressed in water there. So what is the specific gravity of the oil divided by specific gravity of water? That is 1. I know it. Specific gravity of water is 1. So this is indicating the pressure head here. But there is air is there. Up to here I have to move. There is 80 mm air column is there. Air also I am considering here minus 80 by 1000 meters into, I have to convert into the water column there. So I have to take the ratio of the specific gravities, that is the ratio of the densities. Everything I want to convert into the water. So many meters of water. Up to here I had come. Okay, this is at this location. And here the same fluid. Actually here air column also we are considering. We are not neglecting. But usually we neglect the difference in height with the gases. But here I am considering that also. Now if PB is the, now up to here it is come. Here and here the pressure is same. Why? It is a continuous mass of the same fluid, that is air. PB divided by W specific weight of water, that is at this location. Here and here it is same. We are going up. PB by W minus, what is that? What distance is that? 100 plus 100 plus 80, 280. 280 divided by 1000, that is meters. That's all. That is only water there. So many meters of water. Put the specific gravity of water as 1. Specific gravity of water is 1. Specific gravity of the oil we know, that is 0.8 given, and the specific weight of water is 9.81 kilonewton per meter cube. We can get PA minus PB answer. You will directly get in kilopascal. Please note that try to get all the answers of the pressure in kilopascal throughout the FM. For that, the specific weight of water you have to write it in kilonewton per meter cube. Welcome to the chart box, please. Actually, G is given 10, but I have taken more accurately 9.81. It's okay. We will get the pressure difference between PA and PB directly in kilopascal. To get this answer in kilopascal, please keep the specific weight only in kilonewton per meter cube. Keep that point in mind. All the heights, everything you have to keep it in meters. Specific gravity has no units. And in doing this problem, we might observe that every fluid pressure I am expressing it as a water column. If PA is the pressure there, I have converted into the water column by multiplying with the specific weight of water. Here also see that. If PB by W, because this is my datum line. This is my datum line. First, wisely we have to choose the datum line. Here and here I am equating the pressure. One way, this way have come, that is left hand side, and other thing is directly, all this is only water, so no conversion there, directly PB by W minus straight I have subtracted this height. As you are going up, negative, as you are going down, positive. So PB by W minus this height, up to this point you have come, because here and here I am equating the pressure heads in meters of water. See this, it's also a good question there. The reading of all these problems are pertaining to the manometry. The reading of gauge A shown in the figure below is the reading of gauge here, this gauge, rate gauging, you require that. Okay. Now for that, here the reading of gauge A is asking, so I will do the on the gauge basis. Here what is the pressure acting here? Here the pressure acting is atmosphere. That means that is 0 gauge. Okay, everything I will convert in meters of water, that so that finally you can directly get the gauge here. PA by W in meters of water. Here I want to obtain here this reading is equal to, here from here I am beginning the journey, 0 gauge, because corresponding to atmosphere. Here and here it is same, we are going up minus 0.25 meters of relative density mercury, 13.6 divided by 1, because everything I want to convert into the water column, because this value I already know, 9.81 kilonewton per meter cube. So here the 0 gauge, here and here the pressure is same, we are going up by what distance? 0.25 meters, that is by when you are going up minus, but that is a mercury column, I have to convert into the water column. How do you convert? By multiplying with the ratio of the specific gravities. And here it is same, because it is a gas. It is a gas, we can neglect this. Here and here it's same, oil. We are going down. When you are going down, you have to add up. We are going down, add up. What is the column there? 4 meters. What is that column? Oil column. Oil, what is the specific gravity of the oil? 0.8. I have to convert it into the water. So many meters of water. Now you will get the PA gauge. You will get one of those answers. Kilopascal by putting this specific weight of, just multiply this one here. You will get one of those answers. If you understand the manometry equation thoroughly, we can do any kind of manometry problems. See, this one also I do it. It is also a great question. A mercury manometer is used to measure the static pressure at a point in water pipe. Here is a water pipe. At this particular location we require. The level difference of mercury in the two limbs is 10 mm. These are mercury. The gauge pressure at this point. At this point gauge pressure is asked. So what is the gauge here? First you have to show. What is the gauge? It is atmospheric pressure. When it is atmospheric pressure means that is zero gauge. Corresponding to atmosphere, what is the gauge value? Zero gauge. If anything more than atmosphere, if the pressure is more than atmosphere, it is positive gauge. If the pressure is less than atmosphere, it is a negative gauge. Okay, here this is a zero gauge. Now here at this location I require gauge pressure divided by specific weight of water. Here zero gauge, you are going down 10 mm, 10 mm, 10 by 1000 meters, that is a mercury, 13.6 divided by 1, up to here you had come. This indicates the gauge pressure here in meters of water. Here and here it is same, you are going up. When you are going up it is minus 10, again this is only water there, minus 10 mm, 10 by 1000, so many meters of water. Put this specific weight of water as 9.81 kilonewton per meter cube. You will get the gauge pressure there. You will get the gauge pressure in kilopascal. I repeat once again, I want the gauge pressure here in kilopascal. What I do is I will begin the journey here. What is the pressure here? Atmosphere, means zero gauge. From here to here I had come. What distance? 10 mm. We are going down, positive, increase, but I have converted into the meters there, 10 by 1000 meters. But that is a mercury column. I have to convert into the water column because I already put up in my mind everything I want to give the head in terms of water column, because the specific weight of the water is already known. So 10 by 1000 into 13.6 mercury column I have converted into the water by multiplying with the ratio of the specific gravities. Why the conversion into which you are making that liquid, that specific gravity we have to keep it in the denominator. So all this is indicating the gauge pressure here. Here it is same. Why same? It is a continuous mass of the same liquid. Up to here and here the pressure is same. That is indicating this. But I want here at this minus, there is a 10 mm, there is only water there, but anyhow you are under multiple, you are expressing in terms of water. Directly I have subtracted minus 10 by 1000. So multiply this W here by taking the 9.81 right side, you will get the gauge pressure here at this location. I hope you understood the how to write the manometry equation. My preference will be to convert the pressure into pressure head in terms of the meters of the water. Any pressure intensity I am trying to express as a pressure head. Head of what? Pressure head in terms of the meters of water, just by dividing with the specific weight of water, because I know the specific weight of water well. Any pressure intensity could be expressed as a column of any liquid of your own choice. Why my choice is water is because the specific weight of water I always keep in my mind as 9.81. Right? Now we have done well with the manometry. Now I do with the hydrostatic forces. On immersed surfaces. Hydrostatic forces on immersed surface. First case, It is an horizontal plate. I just took an horizontal plate, maybe regular shaped or irregular shaped. Need not be rectangular, but here for time being I am writing the rectangular, but it could be of non-rectangular also. A rectangular plate of area A, horizontal. Specific weight of the liquid is W. This X bar is the depth of the CG, depth of the center of gravity or centroid of the lamina. A lamina means a plate of having a zero thickness, almost zero thickness. It has got an area, but thickness is negligibly small. Maybe regular shaped or non-regular shaped. Then the total pressure, because of the hydrostatic pressure, there is a force exerted. There is a force exerted on that horizontal lamina, which will be exerted perpendicular to the lamina, because if you just look at the lamina, all the locations of the lamina are at the same depth. Therefore, all the locations of the lamina are at the same depth below the free surface, whereas X bar is the depth of its centroid. Below its free surface. Okay, that total pressure or hydrostatic thrust on lamina, on horizontal lamina or plane, that is, will be given by WAX bar, so many kilonewtons. It is the true for all the horizontal laminae, whatever may be the shape. A lamina is having zero thickness but some plane area, maybe regular shaped or irregular, maybe circular or rectangular or triangular, whatever it is. All the locations of the lamina are at the same depth. Therefore, all the locations of the lamina are subjected to the same pressure intensity, because every point on the lamina are at the same depth below the free surface. As such, all of them are subjected to the same pressure intensity. Okay, that will be given by W into X bar. This is the pressure intensity at every location. I already said, to get the pressure intensity at a location inside a static mass of liquid, just multiply the depth of the location with the specific weight of the liquid. So that will give the hydrostatic pressure intensity. So pressure into area, this is W into X bar is a pressure, kilonewton per meter square. That into area will give the hydrostatic force, hydrostatic thrust, which is also called as the total pressure. Total pressure is not the pressure, it is a force. See, total pressure or hydrostatic thrust on horizontal lamina is given by WAX bar. What is the X bar? Depth of the centroid of the lamina below the free surface. But a force will be completely defined according to the engineering mechanics. A force will be completely defined only when you know the magnitude, its direction and the point of application. A force will be completely defined only when you know the magnitude, direction and the point of application. We know the direction, it is acting onto the lamina, perpendicular to the lamina. And how much is that? WX bar. Where is the point of application? For all the horizontal lamina, it acts at the centroid of the lamina. That location is called center of pressure. Remember, depth of center of pressure. So what do you mean by center of pressure? Point of application of the hydrostatic thrust on the lamina. Depth of center of pressure below free surface for all horizontal lamina, H bar is equal to X bar. Remember, for all horizontal lamina, center of pressure and centroid of the lamina coincide. Center of pressure and centroid of the lamina both coincide. Remember this. Case 2. Hydrostatic thrust on vertical lamina. This is a vertical lamina. This is the vertical lamina whose centroid of the lamina here. Supposing this is the centroid of the lamina. Centroid or center of gravity all mean the same for the lamina. It is the location where the area is supposed to be concentrated. G is the centroid of the lamina. Its depth below the free surface is x bar. This is the free surface. W is the specific weight of that liquid, maybe oil or water or whatever it is. Then the hydrostatic pressure variation, if you just see, because the top location is at the A is the area of the lamina. This is the bottommost location of the lamina is subjected to the maximum pressure intensity. This location is because nearer to the free surface, it is subjected to the least pressure intensity. Because we know that as we go deeper and deeper, the pressure intensity will increase. Dear students, if you have any doubts, please keep chatting with me in the chat box. I am just looking into the chat box also simultaneously. Right? This is the pressure intensity variation diagram. But here also the total pressure or hydrostatic thrust on lamina is equal to, here also, WAX bar, so many kilonewtons. Here also, whether it is a horizontal lamina or a vertical lamina, the formula for the total pressure is same. Specific weight of the liquid multiplied by the area of the lamina and the depth of the centroid of the lamina below the free surface. But the main difference is between the horizontal lamina and this one, the center of pressure acts below centroid. It won't coincide with the centroid. The center of pressure will be acting somewhere here. It is the CP, center of pressure. Depth of center of pressure below free surface. Here it is given by x bar plus Ig by Ax bar. Please remember this formula. What is that Ig? Area moment of inertia of the lamina about its centroidal axis passing through the centroid but remaining parallel to the free surface. We have to take the area moment of inertia of the lamina about its centroidal axis which is remaining parallel to the free surface. If this is a free surface, we have to draw a centroidal axis parallel to the free surface. About that axis, we have to take the area moment of inertia, that is Ig. A is the area of the lamina, x bar is the depth of the centroid of the lamina below the free surface. Please remember this formula. For example, I will just give an example there. If this is the free surface, one triangular lamina is there. Okay, say this is 1 meter. Where is the centroid? This is said, this is 2 meters. I am just giving the example that The centroid lies here. Centroid lies at a distance of 2/3 from the top and 1/3 from the base, right? This is from the triangle. This is x bar. When you take the Ig, BH cube by 36, supposing if this is 2 meters, this is also again 2 meters, 2 into BH cube, BH cube by 36, BH cube. This is the centroid. What is the x bar then? X bar will be 1 meter plus 2/3 of 2 meters, because centroid lies 1/3 from the base and 2/3 from the apex. That is the x bar. This is Ig. What is the area? Half into base into height. That is the area of the triangular lamina. That is how we have to analyze the problem. Okay. Now, so we are just giving the example. Now I take the inclined lamina, case 3. Hydrostatic force on inclined lamina. This is a question asked in GATE 2013. Supposing if this is a free surface, this is an inclined lamina. This angle is theta. The true profile of the lamina we can see only in this view, right? When you see from this only, we can see the true profile of the lamina. This is the area A. Okay. The centroid of the lamina is here, G. This is the centroid. This is a projection, no? When you see from the below, you will see like this, the true area. It is a front view, area is like this. If you see the bottom like this is the true shape of the lamina, you can see. The side view will go like this. This is the depth of the centroid of the lamina. Is a free surface. This is liquid, this is the W is the specific weight of the oil, liquid. Here also, the total pressure or hydrostatic thrust. Here also the total pressure or hydrostatic thrust is given by WAX bar. Here also. That means for the horizontal lamina or the vertical lamina or the inclined lamina, for all the cases the formula for the total pressure is same, WAX bar, where A is the area of the lamina, X bar is the depth of the centroid of the lamina below the free surface, W is the specific weight of the liquid in kilonewton per meter cube. For all the three cases, the same formula for the total pressure, but here also the center of pressure lies below the centroid. Why? Actually for the horizontal lamina it is coinciding. Why for the vertical lamina, for inclined lamina it is lying below the center of gravity, but whereas for the horizontal lamina it is coinciding with the center of gravity. The reason is, in the horizontal lamina all the locations are subjected to the same pressure intensity, but for the vertical lamina the bottom half is subjected to the greater pressure intensity as compared to the top locations. That is why centroid is not coinciding with the center of pressure. Center of pressure lies below centroid in for the vertical lamina and for the horizontal lamina also. Here the center of pressure lies here. This is the CP. This is H bar. Depth of CP below free surface is equal to H bar is equal to X bar plus Ig by Ax bar into sine square theta. Theta is the angle made by the inclined lamina with the free surface. If theta is 90, you will get the previous case. Sin square 90 is 1, you will get the vertical laminar case. If theta is 90, this will become exactly vertical, you will get the previous case because sin square 90 is 1. You will get x bar plus ig by x bar, just the previous case. So, for all the cases, the formula for the total pressure is same, but the location of the center of pressure will be different. For horizontal lamina, it coincides with the centroid. Center of pressure and centroid coincides. For the vertical lamina and for the horizontal lamina, center of pressure lies below the center of gravity. That h bar is the depth, vertical depth of the center of pressure below the free surface, given by this formula. Just take a break for 5 minutes. I'll be back. Any doubts, you can post it on the chat box. I will be able to answer. Welcome back to the class. We have seen the three different cases: horizontal lamina, vertical lamina and inclined lamina. But in all these three cases, it is the plane lamina. Okay, lamina means a plane surface having maybe of any shape, like circular or rectangular or triangular, whatever it is, but having almost zero thickness, a plane surface. Like now, I am going to consider a different situation where a curved surface, hydrostatic force on a curved surface, which is slightly more complicated. But if you understand thoroughly, it becomes easy also. Hydrostatic force on curved surface. Like this. This is a free surface. This is all maybe water. This is the curved surface, ABC. And if you just look at the hydrostatic pressure variation, this location being close to this free surface, it is subjected to the very little hydrostatic pressure intensity. But this is the deepest point below the free surface. I already said the deeper points below the free surface are subjected to greater pressure intensity. Because this is the point, it is the deepest from the free surface, it is subjected to the maximum pressure intensity. This is closer to the free surface, lesser pressure intensity. The pressure intensity variation like this. This is the variation of the pressure intensity on the curved surface ABC. Now, how to calculate the total hydrostatic force? So, for that, this is the total hydrostatic force P, which can be resolved into two components, pH, horizontal component and vertical component. If this is the total hydrostatic force P, if P is the total hydrostatic force on curved lamina, on curved surface, total hydrostatic force on curved surface ABC, and pH and PV are horizontal and vertical components, of P, then P will be square root of pH square plus PV square. Then P will be square root of pH square plus PV square. pH is the horizontal component of P, PV is the vertical component of P. That means if I can get the pH and PV, now I am able to get the total hydrostatic force on the curved surface ABC. How to get pH and PV? See how I am giving that. To get the pH, I have to take the component, I have to take the projection. This is on the vertical plane, this is a vertical plane. Onto the vertical plane, I have to take the projection of the curved surface onto the vertical plane. I get some vertical lamina, right? This is a vertical lamina I get. If we just take the projection of this is the curved surface. If we just take the projection of that curved surface onto the vertical lamina, you will get some projected area, right? Whatever the hydrostatic force acting on that vertical, now that becomes a vertical lamina, case 2. So that will become the pH. pH, that is the horizontal component of the total hydrostatic force P. P is the total hydrostatic force on the curved surface ABC. pH is its horizontal component. Then what is the pH? To get the pH, just to take the projection of that curved surface ABC onto the vertical plane. When you take the projection, you will get a vertical lamina, but that vertical lamina will be the projected area, right? So onto that projected area, there is some hydrostatic force will be there, horizontal component. This is a because if it is that projected area is the vertical lamina. Onto that hydrostatic force will be there. That becomes the pH. pH is the hydrostatic force on projected area of curved surface ABC onto vertical plane. You have to take the projection of that curved surface onto the vertical plane. Whatever the hydrostatic force onto that projected area, that will be the pH. Then what is PV? PV is there, no? PV is easy, quite easy to understand. PV will be this curved surface has got certain weight of liquid, certain water content. This is a curved surface ABC. On that curved surface up to the free surface, there is some envelope, right? Onto that curved surface up to the free surface, there is some liquid water is there. Whatever the weight of the liquid contained about that curved surface up to the free surface, that is PV. PV is nothing but weight of liquid contained above the curved surface up to free surface. That is the PV. I know PV, I know pH, I can get the P. So this is the weight of the liquid contained above the curved surface. This is the whatever the weight of the liquid contained in this pink color, no, this colored one. That the weight of that liquid contained above the curved surface up to the free surface, it is nothing but the P. But there is small extra condition here. In case sometimes there may be water below the curved surface instead of above, like this. It is all water. This is some gate. This is all water. There is no water here. Now, I know definitely that what is the direction of the total pressure, because pressure always acts like this. This is all water liquid. So definitely the total pressure direction is like this. That means its horizontal component is pH like this, vertical component PV will be like this. Now how to get the pH? Getting pH is easy. What is it? How to get the pH? Just take the projection of that onto the vertical plane, that directly we can get the pH here. This pH you can get, just get the vertical, this is a vertical plane, no? Onto the vertical plane, just to get the projection. This is the projected area. This is the projected area. Onto that projected area, what is the horizontal component? That is becomes the pH, right? Then what is PV? How to get PV? To get PV, there is no water above that. There is no water, really there is no water here. There is water below that. Then what you have to do? We have to imagine the water above it. This is imaginary water. This is imaginary liquid contained above the curved surface up to the free surface. Weight of that imaginary liquid will be acting as a PV, but in the upward direction. So that is the point, very important point we have to understand. Sometimes in some curved surface cases, there is no water above that. There is no water. But how to get the PV? Then imagine this. The weight of the imaginary water, PV is the weight of imaginary liquid, because there is no water really. There is no water. It is only your imaginary water, virtual water, virtual liquid. Weight of imaginary liquid contained above the curved surface up to free surface. Contained above the curved surface up to free surface, that will be acting as a PV. pH is anyhow, there is really on the left hand side there is water. If you just take the projection I have taken for the curved surface, I have to take a projection onto that vertical plane. This is a projected area. Onto that, what is horizontal, what is the hydrostatic force, that will be acting as pH. Okay. So, if there is no water above the curved surface, you have to imagine that. Weight of that imaginary liquid contained above the curved surface up to free surface will be acting, but in the upward direction. Mind that. Now, let us do some problems here. See this is a problem linked to this. Consider a frictionless, massless, leak-proof plug. It is a gate question. Blocking a rectangular hole. It is a rectangular hole of dimensions 2r is this one, L is the perpendicular direction at the bottom of an open tank as shown in the figure. There is one plug, leak-proof plug is there. The head of the plug has the shape of a semicircular radius. The tank is filled with a liquid. The tank is filled with a liquid of density rho up to the tip of the plug. Here up to the tip of the plug. The gravitational acceleration is Z. Neglect the effect of the atmospheric pressure. Neglect. The force F required to hold the plug in its position. Okay, good question. So, if this is the rectangular plug, right? So, if you just look at this is one curved surface, this is another curved surface. If you just take the horizontal force on this curved surface, it will be from this way, because right. If you just take the horizontal force onto that, it will be like in this. But from the symmetry, both will cancel each other. Therefore, net horizontal force on plug is zero. Why? Because this force and this force are cancelling. Because if you just take it is like this, it is like this. If you just, for this particular portion, if you take the horizontal force acting on that, it will be like this. For this other part, if you just take this horizontal force, it will be exactly. So this force and this force will exactly cancel. From the symmetry, I can say this force and this force will cancel. So there is no net horizontal force. But vertical force will be there. What is a vertical force? There is a water up to here, no? There is a water here. There is a water here. See, on that here, there is a water here. I am drawing. There is water here. There is water here on that. This is, what is that? This water, this is it is a square. Okay, or rather, it is a rectangular. On that rectangular, what is the dimension there? 2r. This is 2r. Height is this is 2r. This is again r. Okay, radius. 2r into r. Total rectangular area. 2r into r. That is 2r square minus 2r square. This is 2r into r, that is 2r square minus this semicircular area, 2r square. I am just calculating this volume, that is 2r square minus, what is the semicircular area? Pi r square by 2. right? Semicircle area is pi r square by 2. So that will give the only the water contained in this particular gap into length into what is the density into rho g. This much weight of the water will be acting on that. So to balance that one, F should be, so answer will be r square can be taken common. 4, if we just take that 4 r square, answer will be A. Answer will be A. That is 2 rho g, 2 rho gl, r square you can take common, 1 minus pi by 4. Answer is A. Because I just calculated this weight of the water. This weight of the water, this weight of the water contained above that. Actually, really there is water above that. So that much weight of the water will be acting downwards. To balance that one, you have to keep apply a force F. Answer is A. Just we have to calculate the force acting corresponding to this water and this water. This water and this water. Okay. This water of length L. Because there is really the water lying above that. Whatever the weight of the water will be acting downwards as a vertical component. To balance that one, whatever the weight of the water contained in this and in this of length L, that we have to calculate. It is an inclined plane. Okay. The minimum mass of the gate per unit width is an inclined plane, inclined at 30 degrees, length 5 meters, inclined at 30 degrees with the horizontal. This is 30. So now this is a free surface. The minimum mass of the gate. So first of all we have to calculate the minimum mass, the weight will be acting vertically downwards, that is mg. So we have to calculate the total pressure. We have to calculate the total pressure P from the formula WAX bar. This is X bar. This is X bar. Centroid of the G. This is G. P will be WAX bar. Unit width we can take. Okay, 1 we can take. W is rho G. Area will be 5 into 1 we can take. X bar will be this vertical height. When this is 30, this will be 30. Okay, this is 30. This will be 60. 30, this is 30, means this is 30, this is 60. This is 2.5. Because it is 5 meters, it is 2.5 meters. We know 2.5, this one, we know this angle. We have to just get this vertical height, X bar. X bar will be cos 60 will be adjacent side by hypotenuse. Cos 60 or sin 30 we can take is equal to X bar divided by 2.5. Now you can get the X bar. I know the X bar, I know the W. W is equal to 9.81 kilonewton per meter cube. Area will be 5 into 1. Okay. Now we know the total pressure, but at what depth it is? Now this is the center of pressure. Forget the center of pressure, you have to get the H bar. H bar formula will be, I know that H bar is X bar plus Ig by Ax bar into sine square 30. Okay. Horizontal with horizontal it is 30 degrees, sine square 30. How to get the Ig? BD cube by 12. B is 1, depth is 5, Ig is the, B is 1 meter width depth, right, per unit width. Depth is 5 meter cube, BD cube by 12, that is the Ig. Area is there, area is 5 into 1. X bar is, already we got the X bar here. Substitute there, get the H bar. We know this, we know the H bar distance now. Now we have to take the moments. Clockwise moment will be because of the weight, and anti-clockwise will be this particular this distance. This vertical distance I know, we can calculate this one based on that angle and then apply the moments about the hinge. You will get the answer. Mg into, supposing if you just take this as y, Mg into y, that is a Mg clockwise moment, should be anti-clockwise moments. It should be equal to the total pressure P into this one. What is this distance? Vertical distance is H bar. This is 60. Cos 60. If you just write the cos 60, cos 60 will be adjacent side by hypotenuse, this one up to here. Okay, this is, we can take this, this is y we have taken already because for the clockwise moment of that mg, and h bar divided by this one, h bar divided by z, we can take this distance as z, that is z will be h bar by cos 60. Now you will get the mass. Answer will be 9623. This is an inclined plane. Mind that once again I am explaining, this is an inclined plane. For the inclined plane, if this is the location of the center of gravity, this is a free surface, just we have to calculate first this x bar. After that, get the total pressure Wax bar. Area will be 5 into 1. This distance is 1. Okay. Then location of that center of pressure. It will be center of pressure location will be h bar. For h bar formula, x bar plus Ig by Ax bar into sine square theta. After getting that h bar and after getting that total pressure, this is the anti-clockwise moment. This is the clockwise moment. Both must be equal. Clockwise moment must be equal to the anti-clockwise moment. Take about this hinge moments. One is clockwise moment and other is anti-clockwise moment. You will get the mass of the gate. Take this dimension of the gate as 1. Ig is BD cube by 12. B is 1. Depth is 5 meters. BD cube by 12. And accordingly, you have to just get this distance there, perpendicular distance. No, this distance is required, because once this is known, this should be known, because this angle is already there, 60. Okay, this distance also should be required to get the moments. Your center of gravity lies exactly at 2.5 meters from this. This distance is 2.5 meters. Simple mechanics question. Okay, now I will introduce the concept called buoyancy and flotation. Questions are being asked commonly on this very age-old principle called as the Archimedes principle. See, whenever a body is floating on the surface of a water, like a boat, these are all the floating bodies, right? Or whenever a body is completely submerged inside a fluid, like a balloon moving in the air, that is submerged in atmospheric air, or a submarine moving under the sea water, it is a submerged body, not a floating. Ship is a floating, boat is a floating. Whether it is a floating body on the surface of a water or completely submerged body, there is always an upthrust exerted over that body. See, for whether a body is floating or completely submerged inside a fluid, there is always an upthrust called force of buoyancy acting on the body, which is trying to push the body vertically upwards. And according to this Archimedes principle, that force of buoyancy is exactly equal to the weight of the fluid displaced by the body. Whenever a body is floating or completely submerged inside a fluid, there is always an upward thrust which is trying to push the body upwards. Body is being buoyed up. So that is called as a buoyancy, force of buoyancy, which will be equal to the weight of the fluid displaced by the body, like this. Supposing a body is floating inside a fluid. Okay. There are two forces acting on that body. One is the weight of the body, gravitational pull, mg, and another is the force of buoyancy acting vertically upward. This is called as the force of buoyancy. And according to the Archimedes principle, this force of buoyancy is equal to the weight of liquid displaced by body. Weight of liquid displaced by the body according to the Archimedes principle. How to calculate that weight of the liquid displaced by the body? It is equal to specific weight of the liquid into volume of the liquid displaced by body. Volume of liquid displaced by body. Then how to get the volume of the liquid displaced? You can easily notice that whatever the volume of the body is there inside the liquid, that much volume of the liquid is displaced. How to calculate the volume of the liquid displaced by the body? Whatever the volume of the body is there inside the liquid, that much corresponding volume of the liquid is displaced. That displaced liquid will have some weight. That weight of the liquid displaced by the body will be acting as a force of buoyancy, but in the upward direction. Okay, force of buoyancy according to the Archimedes principle is weight of that liquid displaced. See, this much liquid is displaced because of the presence of that body inside that liquid. So that displaced liquid will have some weight. That weight is the force of buoyancy acting. Where does it act? Where does it act means the force of buoyancy will be acting through the center of buoyancy. I already said any force will be completely defined only when you know the magnitude, direction and the point of application. You know the magnitude, that is the weight of the liquid displaced by the body. What is the direction? Upwards. Because force of buoyancy always acts upwards, which is trying to push the body upwards. Body is being buoyed up. And how much is that? Where does it act? Means force of buoyancy acts through the centroid of the volume of the liquid displaced by the body. Force of buoyancy acts through the centroid of the volume of the liquid displaced by the body. See, for example, this much body is there inside that liquid, this much portion. Definitely that would have some centroid, right? Whatever the portion of the body that is immersed inside the liquid, definitely it would have some centroid. So, say for example, this is the depth. Suppose the depth of immersion of the body inside the water is h, centroid will be exactly at half of that h by 2. This is the here h by 2. From this is a b, exactly b by 2, exactly h by 2 from the bottom. And if this has got some other dimension, exactly half of that dimension into the figure. So you can easily identify where do the centroid lies. Whatever that portion of the body is there inside the liquid, that portion of the body which is inside the liquid will have some centroid. At that location, force of buoyancy lies. Okay. So according to the Archimedes principle, force of buoyancy is equal to the weight of the liquid displaced by the body. Try to keep that point in mind. Very important point. Okay. I'll just give an example, practical example. Suppose that there is balloon, hydrogen filled balloon, hydrogen gas. It has a thread. You must have seen in the exhibitions there. There is a tension in the thread. This hydrogen gas, hydrogen is much lighter than air. This is an atmospheric air. V is the volume of the balloon. Okay. Totally how many forces will be acting on that balloon? On that balloon there will be 3 forces. Weight of the hydrogen gas plus equipment, rubber equipment, etc. Rubber, balloon is made up of it. And the force of buoyancy upwards, that is weight of air displaced by body, displaced by balloon. How much weight of the air displaced by the balloon? Because the balloon is submerged inside the air. Okay, the balloon is submerged. So the weight of the air displaced is nothing but volume of the air displaced into specific weight of the air. How much volume of the air is displaced? Whatever the volume of the balloon is there. Because entire balloon is submerged in air. How much volume of the air is displaced? Whatever the volume of the balloon. So that is volume of balloon, because entire balloon is submerged in air, into specific weight of air. Okay. And again there is one more force called as a tension. Tension in the thread. 2 downward forces, 1 upward force. The balloon is under equilibrium. For equilibrium, weight of the hydrogen gas plus equipment, rubber, etc. plus tension should be equal to the force of buoyancy. This hydrogen gas is there, it has got some weight, and apart from that, that rubber of the portion of the balloon also will somehow have some weight. This is the volume of balloon into specific weight of the air, from which we can calculate the tension. Generally, equipment of the balloon can be neglected. This can be taken as 0 equipment, because rubber will not have much mass, and from which we can calculate what is the volume of the what is the specific weight of the hydrogen gas. Volume of the balloon into specific weight of the hydrogen gas plus tension is equal to volume of the balloon into specific weight of air. Therefore, tension is equal to volume of the balloon into rho of air minus rho of hydrogen into G. So we will get the tension also. So this is how we can understand the principle of buoyancy. Okay. because density of the air is much greater than the density of the hydrogen, there will be definitely a tension felt in the string. Just one second. So to understand the force of buoyancy, we should only notice that how much volume of the fluid is displaced by the body and multiply with the specific weight of the fluid displaced by the body. Here, being a balloon, entire balloon is submerged in air. So what is the volume of the air displaced? Whatever the volume of the balloon. Therefore, force of buoyancy will be nothing but the weight of the air displaced by the balloon, that should be equal to the volume of the balloon into specific weight of the air. Okay, neglecting the equipment, we can calculate the tension in string. Okay. Look at this. A cylindrical body of cross-sectional area A cylindrical body of cross-sectional area A, height h and density rho s is immersed to a depth h, okay, in a liquid of density rho, and tied to the bottom with a string. The tension in the string is, okay. So, how many forces will be acting on that cylinder? There will be tension will be acting, there will be a force of buoyancy will be acting upwards, because it is displacing some liquid, okay, and also its own self weight. Only three forces: the weight downwards, tension downwards, and the force of buoyancy upwards. For equilibrium of body, weight of cylinder downwards plus tension is equal to force of buoyancy. How to get the weight of the cylinder? H into area, that is the volume, into its density. Volume into density of the cylinder is rho s. Density into volume is the mass into g. This is all the weight of the cylinder plus tension is equal to force of buoyancy. Weight of liquid displaced by body according to the Archimedes principle. Weight of liquid displaced by cylinder. What is the weight of the liquid displaced? How much is that part of the string is there? H part, right? This is only H part is H into area, that much volume of the liquid, into rho will give the weight of the liquid, means whatever the volume of the liquid displaced, only this much volume of the liquid is displaced. What is that volume? Area into height into mass of the liquid, that gives the weight, that gives the mass of the liquid displaced into g. Now you will get the answer for the tension. One of those answers will get. Just get the tension from this. Can easily get tension. This is again a hydrostatic force. A semicircular gate is there. A semicircular gate of depth W. This depth is W, a semicircular gate. So what is the Fx and what is the Fy? Semicircular gate dimension are, this is radius R, and the dimension into the figure is W. It is given clearly. It is like this, right? This is a free surface. So if you just look at the Fx there, if you just take the Fx, how to calculate Fx? Take the projection. Take the projection of that vertical lamina, right? What is the projection there? This is the height of 2r, right? Radius, height of 2r, depth is w, 2r w. Fx will be 2r into w, that gives the area, into the rho, into area is there, w, this is x bar, right? What is that x bar? That is, this is total h, this is given h, area into x bar, w, w will be rho g. So this is Fx. Okay, Fx is very simple. But how to get the Fy? To get the Fy, I divide it into two parts. This part one and this part another. On this part, there is water. There is really water here. There is on this. But on this part, there is no water above that. There is water below that. But for this part, you have to imagine the water up to the free surface, this one. For this, you have to imagine the water up to the free surface. Whereas on this, there is really water, but that will be acting downwards. Whereas this bottom half of the semicircle, it will be acting upwards. So for the bottom half, this is the weight of the imaginary water acting upwards. For the upper part, this is the weight of the real water acting downwards. What is the net water, the net liquid weight? That will be the weight of the liquid contained in this semicircular gate. Fy will be pi r square by 2 into W into rho g. This is answer Fy. Understand? I am explaining once again. This kind of questions are very important. It is a gate. For the bottom part, there is no water above that. Only below that there is water. So for this bottom part, what you have to do? You have to imagine the water up to the free surface, above the curved surface, up to the free surface. But for this upper half of the semicircular gate, this upper half, there is really water is there. What is it? Welcome back to the class. I'm just discussing how to calculate the Fy for this semicircular gate. If you just look at this part really there is water. But when you look at this bottom part, there is no water above that. I already said, whenever there is a curvilinear surface is there, if there is no water above that, but there is water below that. Look at this, there is water below that. Then what we have to do to calculate, how to calculate PV, vertical component. Imagine the water contained above that curved surface up to here. I am talking about this portion. Imagine that water, but whatever the weight of the imaginary liquid contained above that, this one will be acting upwards like this. For this imaginary water will be acting upwards. But whereas for this portion of the gate, there is really water which will be acting downwards, contained above that. So definitely, but that imaginary water content is more. So net force will be acting upwards, corresponding to the this whole weight of the water minus this portion. So whatever the water contained in this semicircular gate, that is by. Hello, 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 hello. So to calculate the Fy, I have just subtracted the weight of the water contained above this one acting upwards minus the weight of the real water. So that will be the Fy, that is the weight of the water contained only in this. That is pi r square by 2 into W. W is the width of the gate into the rho g. That is the specific weight of the liquid. So this is the answer. So one thing we have to understand is whenever there is water below the below the below the curved surface instead of above, we have to imagine. We have to imagine. This is all imaginary water. Above the curved surface, up to the free surface, whatever that imaginary water is there, all this is will be acting upwards, not downwards. Will be acting upwards. Conditions are given. Assuming no disturbances due to wind, the maximum allowable weight of balloon material and rope required to avoid the fall of the balloon. Okay. So how many forces will be acting on that? The only two forces. One is one is weight of the helium. Second thing is the weight of the equipment. Weight of the equipment downwards. Weight of the rubber, no? Rubber weight of the balloon material downwards plus weight of the helium, that is also downwards. It should be the force of buoyancy upwards. What is the force of buoyancy upwards? Weight of air displaced. Weight of air displaced. That is the volume of the balloon. Volume of the balloon into specific weight of air. Specific weight of the air you have to calculate. That is rho of the air is equal to P by RT. Atmospheric pressure is 100 kPa divided by 0.289 into temperature is 15 plus 273, that is the density of the air.
Okay, ideal gas equation. Similarly, density of the helium, because weight of the helium means I require the density of the helium is equal to pressure is 100 kilopascal, gas constant is 2.08 into 15 plus 273. All temperatures must be kept in Kelvin. So weight of the helium I got. How do you get the weight of the helium? Volume of the balloon into density into G. Okay, no? Volume of the balloon is how much? Spherical balloon, that is 4/3. Volume of the balloon is 4/3 pi r cube. Sphere, no? 4/3 into pi r cube. Radius is 5. Now I know the volume of the balloon. Weight of the helium is density of the helium into volume of the balloon into G. Weight of the air, already volume of the balloon is given. Weight of the air will be, weight of the air displaced will be volume of the balloon into rho of the air into G. That is also known, and a weight of the equipment can be calculated very easily. But take care of the units there, because he has asked in newtons only. This is also newtons.
Hello, hello. Now, in this particular problem, on the balloon there are three forces. So in this problem, which is given in the gate 14, on the balloon there are three forces acting. One is the tension, which is tension in the rope. Other is the force of buoyancy, which is nothing but the weight of the air displaced by the balloon. According to the Archimedes principle, force of buoyancy acting on any body is equal to the weight of the fluid displaced by the body. Here the balloon is displacing air, atmospheric air, which is at a pressure of 100 kPa and temperature of 15 degrees Celsius. So how much air is displaced? Whatever the volume of the balloon is there, that much volume of the air is displaced. That means to calculate the force of buoyancy, that is the weight of the air displaced, volume of the balloon, that is the volume of the air displaced, into specific weight of the air. Specific weight of the air means density of the air into G. How to get the density of the air? By using the ideal gas equation. Rho is equal to P by RT, where R is the ideal gas constant. Okay. Similarly, weight of the helium is nothing but the rho of the helium into specific weight of the helium into volume of the balloon. Volume of the balloon we can calculate because it is a spherical balloon, 4/3 pi r cube into rho of the helium. How to get the rho of the helium? Helium is also an ideal gas, P by RT, but gas constant of helium is given, that is 2.08, whereas the gas constant of air is 0.289. So we can calculate the density of the helium, and we can calculate the whatever the weight of the helium. Now we can calculate what is the weight of the equipment by substituting here. So very good question, given in gate only. Look at this. The large vessel shown in the figure contains oil and water. A body is submerged at the interface of oil and water such that 45% of its volume is in the oil, and the rest is, that is remaining 55% is in the water. Volume we talk about. The density of the body is dash. Specific gravity of the oil given, density of the water is given, acceleration due to gravity. Simple thing, from the Archimedes principle only we can answer. Okay. Weight of the body, it is under equilibrium, right? There are only two forces. Weight of the body should be equal to the force of buoyancy will be acting upwards. Whatever the force of buoyancy is, what is the force of buoyancy? Metallic body is displacing 45% of its volume in oil. Okay, now in this particular problem,
this metallic body is under equilibrium of two forces, actually three forces, precisely speaking three forces. One is weight and the force of buoyancy exerted by the oil, force of buoyancy exerted by oil plus force of buoyancy exerted by water, because this body is displacing 45% of its volume to the oil, 55% of its volume displacing the water. So what is the weight of the body is asking. Okay, the density of the body is, that is volume of the body into density of the body is the mass into G. All this is the weight of the body is equal to force of buoyancy exerted by the oil. What is the force of buoyancy exerted? 0.45% of the volume of the body into rho of the oil into G plus 55% of the volume of the body into rho of the water into G. Okay. I think volume of the balloon, our body gets cancelled there. So everything is known there. Rho of the oil is rho of the oil is 0.7 and density of the points rho of the oil is 0.7 into 1000. The density of the water is there, G is there, everything is there. G also gets cancelled. In fact, you will get the rho of the body. Simple question given in a gate only. This weight of the body is cancelled by the force of buoyancy exerted by the oil, which is nothing but the weight of the oil displaced. What weight of the oil? What is the weight of the oil displaced? Volume of the oil displaced into specific weight of the oil. Okay, or density into G. 55% of the body is displacing water. That is also exerting some other force of buoyancy. Weight of the water displaced. So to calculate the force of buoyancy, we require the weight of the fluid displaced by the body, for which how much volume of the body is immersed inside the fluid we have to catch up. While doing the problems of the buoyancy and flotation, please note that how much portion of the volume of the body is inside the fluid, how much of the volume of the fluid is displaced, multiply that one with the specific weight of the fluid. So after this, there is some conditions of equilibrium for a floating body. You have to remember that. Conditions of equilibrium for a submerged body, like balloon. Like for example, if you just take the balloon, okay, if this is G and if this is B, B is the center of buoyancy through which the force of buoyancy acts. G is the center of gravity through which the weight of the body acts. G is the center of gravity, B is the center of buoyancy. B is the center of buoyancy through which the force of buoyancy acts. G is the center of gravity through which the weight of the body acts. If the balloon is given a slight angular displacement, because it is completely submerged body, the locations of the G and B are fixed. They will not be changing with reference to the orientation of the body. The location of the body, the location of the center of the buoyancy with reference to the orientation of the body will not change, because it is already completely submerged inside the fluid. For a completely submerged body like a balloon or a submarine, even though the body is given a slight angular displacement, even after that, the locations of the center of buoyancy and center of gravity will not change. Now, if you just look at this figure, there is a balancing couple being developed, because two equal and opposite forces acting at a distance, they create couple and they try to get back the balloon to its original position. So this is called as this condition is called as a stable equilibrium. So condition for the stable equilibrium is G must lie below B. G must lie below B. Location of the G should be low. So you can see that in the exhibitions you must have seen this kind of a toys, right? If you just look at the bottommost pouch, there is some wet sand will be there. Some wet sand, they fill it with a wet sand so that the location of the G is always maintained below. So whatever may be that toy is hit, immediately it will get back. So the pouch will be there, small pouch at the bottom of the toy, which contains wet sand. Because of that extra mass kept, G is always brought downwards. The condition, remember that G must lie below B for stable equilibrium. Supposing if G goes above and B goes below, means if you give the slight angular displacement, there will be a overturning couple will be developed. Whereas now here there is a balancing couple, right? There is a balancing couple. Whereas if it is a B lies below G, B is, supposing if G lies above B, then unstable equilibrium. These are the questions that may be asked in the gate. Unstable, since overturning couple developed. Overturning couple develops. If B and G coincide, then neutral equilibrium. No couple developed. No couple developed and the body assumes the new position. It won't come back, it won't overturn. No couple developed and the body assumes new position. That is called as the neutral equilibrium. So the conditions of equilibrium for a completely submerged body like submarine and balloon will be decided by the relative positions of the center of gravity and the center of buoyancy. You can see here the toy, for the toy case, because of that wet sand kept in the pouch, the location of the G is always maintained at the bottommost position, so that whatever the way you hit with the toy will immediately get up and come back to its original position. So this is for the submerged body. But for the floating body like a ship or a boat, the conditions of equilibrium will be different. So they will be based upon the location of the metacenter and the center of gravity. So the relative locations of the metacenter and the center of gravity will decide the conditions of equilibrium for a floating body. So for that case, I will take it in the next class. Meanwhile, if you have any doubts, please try to post it. Today's class is over. I will be waiting for your chat box. I am looking into the chat box. If anybody is there in the class, please try to chat with me for the doubts. I am waiting here for your doubts. Please, dear students, if you want to chat with me, I am looking into the chat box. Please welcome onto the chat box. Anyone in the chat box, please? Dear students, anyone please? Please do come onto the chat box to discuss with me pertaining to the topics I have covered today.
Okay, okay, dear students. Good night. Crux classes, after going through the my video lectures which were uploaded in the Msigma Gokulam app, I had given a detailed videos of fluid mechanics for about 60 hours. Please go through them one after another, and then if you come to the Crux class, it will be much more useful for you. Okay, good night.